In the last video, I've talked about how, in order to make use of Faraday's law to calculate the voltage in a sort of a logical way, we should think about the direction of the coil, right? Direction of, say, a particular side of the coil, and that when that side changes direction after you rotate it by 180 degrees, we should also change the sign of the flux when we need to use this flux to calculate the voltage using Faraday's law. Now this rule, if you like, can be done in another way, which could be more convenient. If you recall from a few videos ago, I've mentioned that you can actually we can actually calculate the flux using this formula, using the formula B A cosine theta, where, if you remember, I said that theta is the angle between, say, the magnetic flux and the perpendicular to the area. So, for example, here the angle, the theta, is this angle between the green line and the magnetic field line. So in this case, the theta is actually 0 degrees. Okay, and in this case, the angle is this angle, which is 90 degrees. In this case, the angle is the angle from there to there, which is 180 degrees. So if you actually use this formula, you find that when you're here, when you're in this position, theta is 0. Okay, so and cosine 0 is 1. So this would be BA cosine 0 degrees, and cosine 0 degrees is just 1, so this is just BA. And in this case, you have BA cosine 90 degrees. Alright, if you remember, the purpose of adding the cosine is to allow us to find the components of B, of the magnetic flux density, to find its component along the direction that is perpendicular to the surface or to the coil. So in this case, the flux is along the surface, so there's no component perpendicular to the surface, and we know, and as we already know, it is 0, and it disagrees with cosine 90 degrees, which is also 0. And when theta is 180 degrees, we have BA times cosine 180 degrees. And cosine 180 degrees is minus 1, so we should have a minus sign here, which agrees with the rule that we made up just now. Right, and that has a minus sign there. So using this formula actually incorporates that rule automatically. It means that if we take the flux to be BA times cosine theta for this simple coil, we can basically we would not actually have to think of that rule, think of this plus and minus direction rule directly. Alright, we don't have to think about it. All we need is to just use this cosine theta formula. And that makes things a lot more convenient. Now, not only does it make things more convenient, it also makes it possible now for us now to make use of this formula for the flux to actually calculate the instantaneous voltage that is produced by the rotation. You see, previously, all I could do was to say, right, after it rotates by, say, 90 degrees, if the time taken is 0.005 seconds, then I put it into Faraday's law and calculate the how fast it changes during this time, and then I get the voltage induced. But actually as it rotates from 0 to 90 degrees, the flux may not actually change uniformly, and as you see, the formula is cosine theta, and cosine theta is not a straight line. Alright, the cosine graph is not a straight line. So as it rotates from 0 to 90 degrees, right, assuming that it rotates at uniform speed, uniform angular velocity, I should not really expect to get a constant induced voltage. So what actually does the induced voltage look like? So this calculation here, all it gives is an average value between 0 and 90 degrees. So in between, the actual voltage at any particular instant in time might actually change. Okay, and that's what I would like to look at in this and maybe the next video. So let me start this off by looking at the general case when the angle is when the angle can be just any value of theta. Right, so suppose that I have magnetic field lines in these directions. So that's the magnetic field, and let's say it's 1 Tesla again. Still, now suppose that I have this time I have a coil that is a square loop that is tilted at some angle. So it's the same square loop, but it's neither vertical nor horizontal, it's at some angle. And I'm going to again draw a perpendicular to the square loop so I can follow its motion. So this is a perpendicular arrow. Okay, and in order to calculate the flux, we need to know the angle. We need to know the angle at a particular time, particular point in time. And we know that the flux is given by let's see, flux is given by B A, where A is the area of the square loop, times cosine theta. Okay. Now, I would like to express this in terms of time. Okay, because we, according to Faraday's law, the induced voltage is the rate of change of the flux with respect to time, of course. So I really would like to know how the flux changes with time, and we can express theta in terms of time, if you think back to my videos on circular motion, okay, so suppose that this coil is rotating. So if it's rotating, it's a circular motion, and suppose that it's rotating at uniform angular velocity. So that would be omega. Now remember what angular velocity means. Angular velocity is the angular displacement. That means the angle that it rotates divided by the time taken. Okay. Now let me write this more clearly. This is theta, not 0. That's theta over the time. So it means that the angle theta is equal to angular velocity times time. And this gives us a simple way to write the flux in terms of time. It is just BA times cosine omega t. So now we have phi in terms of time. And if you look at this, you see that it is cosine. It is a cosine function, cosine of a number times t. Now the omega here is the angular velocity. We can assume that it's a fixed velocity. Okay. If I think about sketching a graph of this, it would just be a cosine graph. Okay, and we know what a cosine graph looks like. Now a cosine graph looks like this. That's a cosine graph. It starts from a maximum value, comes down to 0, goes negative, and go up, down. Okay, and the amplitude. So we can take over all that we learned about wave motion and circular motion. So the amplitude would just be the number that multiplies the cosine function. So that would be BA. That would be the maximum value. And then we have this idea of a period, the time for one cycle. I'll call that a period. And from circular motion, we know that the period is equal to, let's see. The period is the time for one cycle, and we know that one cycle should correspond to when the coil rotates by 360 degrees, because then it comes back to the original position and the motion repeats itself, so the flux also repeats itself. Now 180 degrees is 2 pi radians. Okay, so in the time taken for one cycle, this will have rotated by 2 pi radians. If you remember, we need to use radians for this angular velocity formula. And so we have an expression that relates the omega here in this formula to the period, the time for one cycle of the motion. Now, so what you can see here is something that looks very similar to what we have learned from simple harmonic motion. And in the next video, I'm going to talk more about how we can obtain from here, how we can obtain the voltage using the methods that we have learned from simple harmonic motion.